Hi, everyone. Today we're going to investigate some coronavirus statistics from the beginning of the lockdowns last spring. So you can see this data starts on February 7th and then goes until March 10th. And obviously things have changed since then, but this was what we were working with at the time. So we wanted to see what was going on with the data of the cases outside of China back in February, March. So first, I want you guys to go ahead and do numbers 1 and 2 using Stapple.com and your knowledge from the past couple of classes. Make the scatter plot, then make the residual plot, and discuss whether a linear model is appropriate for the data. Pause the video, come back to it when you've done that. Okay, so here's what you should have gotten for your scatter plot and your residual plot. We can see in our scatter plot we have a clear curve, and then I put the x-axis as days since February 6th because February 7th is the first day, and so February 6th would be day 0. And you can see a definite curve there, and then when we go even further to a residual plot, there's a clear pattern. And remember, when there's a clear pattern in the residual plot, then a linear model is not appropriate. So we can use both of those combined to discuss or decide that a linear model is inappropriate for this data. So let's talk about what is appropriate. What type of model do we think best fits it? You guys can think about this, but many people have in the nation already described the growth of the coronavirus as exponential. And mathematically, that does appear to be the case by looking at how it gets really big off to the right. There are many options, but this is a good guess so far. The general form, if you don't remember from your previous maths, is y equals a times b to the x power. And so that gives us, when your variable x is in the exponent, that's an exponential model. Algebraically, the inverse of that is a logarithm. And so how can we transform our data? What I want to show you guys is some algebra behind the whole process. Then what we'll do is take the log of both sides. So that would be log of y equals log of a times b to the x. Then we can use some log rules that we learned back in the day to split up this product and then bring the exponent to the front. And so what we end up with is log of y equals log of a plus x log b. What I want you guys to notice is that the x is not inside the log and the y is. And so what we can do is take the log of all the y's, and that will help us transform our data into a more linear model, because now we have our a, this is kind of like a, and then log of b is like our b. So we really have like log of y equals a plus bx. Now you guys can use that knowledge to do 4 through 7, and if you feel like you can do 8 to 9, go ahead, but I do need to help you with number 6 first. So go ahead and try 4 through 7, pause this, check on number 6 before you continue to 8 and 9, since you'll be using your answer to that before. Okay, so if we take the log of all the y's, let me just make sure you guys know how to do that first too. So if you weren't sure, letter 3D, we ended up saying we're going to take the log of all the y values, and so it told us to do that in the table on number 4. So what we did was log of 330, log of 481. It's just a button in the calculator that you can click. So I'll just show you really quickly. If we just hit log 330, then that's where those numbers came from. And we just did it one at a time. I just rounded to 4 decimals. You can round to any amount. There's no wrong answer there. As long as you do, I would say at least 2 or 3. And my new scatter plot, when I put those log values in Stapple, it looks much straighter. So that did straighten it out a little bit for us. Then when I did the LSRL in Staplet, this is what I got. Y hat equals 2.2988 plus 0.0672x, where x is the day since February 6th, and y hat's the predicted number of cases. But the problem with this is I already have the exact same variables defined on my other scatter plot, and so we need to add a log in front of the y hat because we took the log of all the y's, which means we need to show that in our equation. So we're going to add the log in front of the y hat. Remember, when we transformed it algebraically, the y was still inside the log, so that's really important. Number 7. Number 7 was for you to see if it was a good fit. So we did another residual plot. And so I did notice that my scatter plot was a lot straighter, but the residual does still show a clear pattern. So even though we straightened out our original curve some with transforming it, we still can get a little better. So now you can try 8 and 9. Now that you know, and if you need help, just unpause the video and I'll talk about number 8 specifically. Okay, on number 8, we're asking you to solve for March 10th. So on March 10th, I just went back to my original. That was day 33. And so that's where x equals 33 came from. If you added the log back in like you were supposed to, then what you end up with is log of y equals 4.5164. So to get rid of a log, you have to raise both sides. You have to raise 10 to both sides. And so 10 to the 4.5164 is equal to 32,839.76 cases. I'll debrief that in just 1 minute to show you how to do it in the calculator. I can just show you right now. The way I got that was you hit second log, and then I typed the 4.51. I think it was 64. Where did it go? There. I think it was 64. That was right here in front of me. Yeah, so that's where I got that. Okay, sorry about that. Now for the residual, you should have been able to do that observed minus predicted. Our predicted was too low because it was lower than the observed, and so we got a positive number. All right, so what we're going to do now is I'm going to go ahead and debrief with my red pen a couple key things about this activity. And so if you're just joining in from class, then this is a great place to start. And just go back to the beginning and we'll start to do a couple debriefs and then we'll be done. Okay, so there's nothing to really do on the first page. Everything's pretty clear there. But what we do here on the second is say that if x and y have an exponential relationship, then x and the log of y are linear. So that's what our correlation will describe between x and the log of y. Okay, next, took all the logs. You have to have the log in front. So this is key that you added the log back in. And then just so you guys know, our scatter plot, our residual plot did still show a clear pattern. And so I did this, I just did some investigating with what the best model would be. And it actually ended up being a quartic model with y equals a times b to the x to the fourth plus, or a times x to the fourth plus b times x to the third, c times x squared, etc., which is not part of our stats course. So there was an even better model out there, but that model isn't one that we do in AP Stats. I wanted to tell anyone that cares about that kind of stuff what the real model was for this exact set of data. Okay, so then here to solve, you hit second log. So I'll just put second log is one way to get that. And then our predicted cases were 32,839. You guys know residuals already, so we're not going to debrief that. Now we're going to go ahead and take some notes on the big ideas page. So first, we have 3 types of functions in AP Stats that we deal with. We have linear, which is x versus y on the scatter plot. Power, where the linear scatter plot, we can take the log of x and the log of y are exponential. So let's just write the forms for each of these. This one is y equals a plus bx. This form is going to be equals a times x to the b. And on this one, we get y equals a times b to the x. And so algebraically, what happens is this is already linear. But for the power, if I log both sides, the x and the y end up in the log. And so it's linear between log of x and log of y. And for exponential, when I log both sides to transform the data, it's linear between x and the log of y. And so that's something you have to kind of memorize. The activity was going to help you see it a little bit. And here's some examples of things you might have to solve that you don't know maybe from your previous classes you might have forgotten. So to make predictions, we plug in our x and solve for y. If your y is inside of a log, then you have to second log or second natural log to get it out when you're solving. Some other solving ones will be a little bit easier. So the last thing I want to show you, well, before the check your understanding, I want to show you guys a little connection. So let's look at these scatter plots originally, and I'm going to bring them over. Okay, so first, this was our original scatter plot right here, and it has a clear exponential curve. And so our equation was y equals negative 7900.2611 to the x. I'm just going to kind of write this down for us. Okay, 985.2833 x. So that's not actually useful to us at all because that was not the correct model. So what we do instead is we can look at, how about let's check out the exponential model. Let's calculate another regression. So I'm going to write that equation down on my paper, and you guys feel free to as well. We have y equals 198.9843 times 1.1672 to the x power. And so that is our exponential model. So the first equation is irrelevant because that was not the correct model. According to us, we did everything exponential. So then what I want to show you is after we've taken the log of all the y values and done this graph, then when we do a least squares regression line, that became log of y hat equals 2.2988 plus 0.0672x. And so what I want to show you on my calculator is I want you guys to see how these are related. So if I take the log of 198.9483, remember I could log both sides, then I get log of y hat equals log of 198.9843 plus x log 1.1672. Then what we should be able to see is that these values equal each other right here and here. Oops. So that's just a quick little explanation of how it works mathematically, that when we take the log of the y's, it does give us a linear relationship that we can use because our class only does linear associations and not anything else. So our goal is to transform everything from nonlinear to linear. Okay, now pause here and do the check your understanding. If you didn't understand any of that, by the way, it's okay. You just need to know these main things, right? So try the check your understanding. I am going to show you one quick thing about it. You might not know how to do this yet, but this table is very confusing to read. We can cross this off, this off, and then we'll never use the adjusted. And so this is our A, and this is our B. And then if you read the whole problem, it tells you all about it, that our length is x. And so just hope you notice this cubed thing. That means that we'll write our equation as y hat equals 4.066 plus 0.0147x cubed. And so that is where you get the equation for the least squares regression line, where x is my length and y hat is my predicted weight. And so to do letter B, they asked us when the length is 36, what's the predicted weight? So I plugged 36 in for x. I didn't have to do any crazy solving. I could just put that all on my calculator and get 689.91 grams. If you need any more help with these tables, we'll go over them tomorrow as well. So no worries. They're not any in your homework like that. But you guys have a great day. And please let me know if you have any questions. Look forward to seeing you next class. Thank you.